Well, I bought a grater blade, Tractor Supply. It's a County Line brand, and just got finished grading the road, get some of the snow off. But the grater blade is about $340, and it doesn't look real beefy. So I thought I'd take some measurements and just kind of draw it up 3D and maybe do a structural analysis on it just to see how strong it is and what load it could take before the blade might bend. So let's go inside and I'll show how I can do this. So I took some measurements of the grater blade on the B414 tractor. It's a County Line grater blade. Bought it at Tractor Supply. And some of the basic measurements you can see right here. That'd be the blade support, about 14 inches tall. And then what I would do is actually extrude that out as a surface and just kind of build up the whole frame. Took all the measurements, built in the support brackets, 3-point hitch features, and then the next thing I did was I wanted to see what kind of load that this grater blade could take before it bends. So the tractor that I have is an International B414, and if you actually go to the internet and type in B414 tractor PDF, you can actually bring up some specifications for that tractor, and here is the diesel tractor. And that information comes from University of Nebraska. And if you scroll down, you can see that the tractor is about 40 horsepower, just under 40 horsepower. And the drawbar pull force is around 2,300 pounds. That'd be 4th gear, low range. So we know how much the tractor can pull. We want to see how much load the grater blade could actually take before it bends. So probably max load 2,300 pounds. And let's take a look at if we put a force load at this edge of the grater blade. We want to see how much load it could take before it actually starts to bend. So the next thing we do is actually import these surfaces into ANSYS software. And the software I'm using here is SolidWorks. So if I go to ANSYS, I can import the geometry, and this is what you're looking at here. The geometry is highlighted here. Here's the blade. The material that I used was just basic mild steel. Yield strength around 30 KSI. So I imported the geometry. Next thing I did was add some boundary conditions, fixed all the features together, some weld joints. Here you can see some weld connection joints. Just some basic boundary conditions, constraints. And once we added all that, then I went in here and actually started meshing these surfaces, extrude them out to a certain thickness, and there you can see the mesh. third point hitch. And I did leave out the swivel joint. I just made it a solid feature just to make the software run a lot faster, just to get some basic information on the blade strength, how much load it could take. So once we got it all meshed, there's some properties that you can actually check on the geometry, just to check the weight. And after I've got this meshed and used the appropriate density, it weighs about 193 pounds. And that's real close to the actual weight that's on the spec sheet of this blade. So we know we got it pretty close in terms of dimensions. So now I've been running this analysis. See if I can click on here and show you some loads. So here's the force that we added, and right here on this edge. I tried different forces. I started out with 1,000 pounds, 1,500 pounds, went on up to 2,000 pounds on this edge. And that would represent, maybe if you're grading out a ditch or something, and you hang, a big rock or a root or a tree stump, how much could that edge actually take before the blade actually bends? So I ran the analysis, and so the first part here shows the results of 1,000 pounds load. The red represents high stress areas. Blue represents low stress. So you can see that with 1,000 pounds of load on the edge, you'd actually have some high stress areas around this bracket area. Some here at the edge of the blade. And if you turn it, you can see it's bending a little. You can see a slight bend down in here. And then if you release the load, you can see how much deformation this corner, and it took a set of about 80 thousandths, so it did bend. That's at 1,000 pounds of load. So going up to 2,000 pounds, you can see that now you're starting to stress the support member up here and some other areas of the blade. Looks like the bottom bracket is taking a lot more load at these weld joints, and the blade is starting to bend even more. And then if you release the load, you can see that corner now has deflected 137 thousandths. So now it's bent even more. Not a lot, but you'll be able to see that. Maybe looking down on top, you can see a slight bend. This is a displacement plot. So now we actually was looking at a load I believe that right there is actually 1,500 pounds of load. So we did 1,000, 1,500. 1,500 load took a half-inch set. Might have that labeled wrong. And then we went on up to 2,400 pound load. And you can still see the bracket, support bracket here on the back of the blade is highly stressed. And the deflection is on up to now a half-inch with a 2,400 pound load. And that's once the load is released, your blade has actually deflected about almost ½ inch. So the blade is not real strong. It is spec'd in to be mounted on small tractors, 35 to 40 horsepower. This stress plot that's the 2,400 pounds load. And then if we want to, you can actually animate this blade just to see kind of how it is loading up and unloading. So I'll just click on the animation button, and there you can see it's animating. So if we take a look at the top view, you can see actually how it deflects under the 2,400 pound load. It really torques this top cylinder, that mounting point of the blade, which right in here. So you got a lot of deflection, torsional deflection from that 2,400 pound load. So if we stop the animation, it does spring back, doesn't take a permanent set. Let's see, if that's 2,400 pounds, that's actually right there is probably the 2,400 pounds. And that is time step number 5. That's 1,500 pounds. So once you kind of look and see how this blade is deflecting, you can actually go back in and actually model in maybe a support member. So here, I actually modeled in an L bracket on the back side. So there's the bracket. And then we can actually import that geometry into a new analysis. And there's the model for the bracket. And there is the mesh of the bracket. And you can actually run this several cases. You can move the bracket up, down, but we knew it was high stressed in this area, so I thought, well, let's put a bracket, support bracket along the length of the blade just to see how that would strengthen the blade and maybe keep it from deflecting much. So what I'll do here is I'll actually have some plots of the results of that. And deflection after the 1,500 pounds is about 0.169 dead edge. At the 2,400 pound load, once that load is released, the set was around 1/4 inch, so it did help. If you remember, the other model without the bracket was deflecting about 1/2 inch after the load. So now you can see that this software can be used actually to design the whole grater blade You can check the loads, stresses in material, check your 3-point connections here, see if they're highly stressed. Design new brackets if you want to make it lighter if you could, or heavier. And that's pretty much it. That's how this software works. So what we looked at this here, it shows that for this size tractor, which is International B414, this grader blade is, it's probably okay to use for this type tractor. 40 horsepower, 2,300 pound pulling force. So you'd probably, if you hung something, you would bend your grader blade. So you definitely don't want to mount this grader blade on a bigger tractor. So this grader blade matched up with this tractor, this light duty work, you'd be okay. And that's all we have. If you got any questions, just maybe make a comment and I could probably follow up with more detail.